And this is Brother Guy, of course. So. Now, I got the idea of inviting him because I read a great book called Turn Left at Orion, and I'm still trying to figure out turning left. Are you going to come up with a sequel, like Turn Right at Sagittarius?
There is a Turn Right at Orion.
Oh.
Somebody else wrote after my book.
Oh, I see.
It's a fine book, but its sense of direction is terrible.
Right. Well, you could go straight ahead to it. But anyway, it's a great book. As a matter of fact, I got it right here. You can sign it for me?
Stick it in my pocket then.
We got a minute to kill.
All right.
Okay. Thanks. So anyway, it's a fantastic book. It's one of the ones I've read, and Brother Guy's written a lot of research papers as well. We're very lucky to have him because he's traveling all around the world all the time. Every time I emailed him, he was like in Portugal and Spain and everywhere. So we're lucky to have him here and to speak with us tonight. So, okay, well, thank you. And without any further ado, here's Brother Guy.
Well, you probably know that science is never done alone. Science is done in collaboration with many people. It's one of the odd things that the stereotype of the nerd is the guy with no social skills, but in fact scientists and engineers are the one group of people who must work in teams. And this talk is also a team project. My co-author is a fellow named Mark Sykes. Mark was at the University of Arizona soon after I left, and he and I share many traits in common. We were asked to debate whether or not Pluto was a planet. And since you know what I look like, Mark also sings in the opera. And in fact, it's been thought that the two of us resemble yet another famous Mark is the director of the Planetary Science Institute in Tucson, and is a wonderful scientist and a rather frightening character because at one point when he was afraid he wasn't going to get a grant renewed, he decided to go to law school. So he's both a planetary scientist and a lawyer, and passed the bar in Arizona. So that makes him a really difficult person to debate. It's further complicated by the fact that the IAU made a decision about Pluto 3 years ago. I was involved in that decision. I argued vigorously on a particular side. My side lost. And then, as an officer of Commission 16 of the IAU, I then had to defend the decision that I'd argued against. So my initial reaction is to be very favorable to Mark's ideas, because Mark and I, in a certain sense, agree completely. What is a planet? That's a wonderful question. That was really the heart of the whole Pluto issue, whether or not Pluto is a planet. What are we doing when we ask the question, what is a planet? What we're trying to do is to group things together and decide what makes these objects all the same and different from that. And it's less obvious than it seems. It was actually an entire thrust of medieval philosophy and great debates between Thomas Aquinas and his followers and Don Bosco and his followers and who's the Occam, William of Occam and his followers. Each of them had different ideas of can you say that there is a thing we call a car, and we all know what a car is, even though cars come in various different shapes, and that's not a car. It is a point of philosophy which is, it's both amusing and profound at the same time. The other question, which is a question of this title, was, so what? I remember going to a scientific talk once, a seminar like this, and the learned astronomer talked for an hour, and at the end, one of the other learned astronomers raised the hand and said, I have a question, so what? I mean, you've been talking for an hour, why should I care about what you've been talking about? And while it's an irritating question to ask, it's mostly irritating because it's really difficult sometimes to answer. Why are we concerned? Classification is one of the things that science does. Classification is the way that we decide whether or not we really understand what it is we're talking about. Classification also organizes the way that we study. the materials. It means when I know I'm going fishing, I pack a fishing rod. When I know I'm crossing the desert, I pack water. If I take a fishing rod to the desert, that's evidence that I haven't properly classified the region that I'm going to and the things I'm likely to find. So a classification of whether something is a planet or not both controls the way we think about it and the questions we ask about it and the way we go about coming up with answers for those questions. So classification is a fundamental aspect of doing science. I see there's a bunch of people standing in the back. In fact, there's an overflow room if you want to be able to see me from there. So, Mark, being a geologist and a planetary geologist, asked what are the characteristics of a planet? Well, planets have atmospheres, though some planets don't have much of an atmosphere. Mercury doesn't have much, but it's still a planet. Planets have geology. Things are going on the surface of a planet besides the fact that they've just been hit by other small planetoids. So, what are the traits of a planet that all planets seem to share? And that you can tell from looking at an object in a telescope whether or not it shares those traits. This is an example of the realm of things that we know exist in our solar system, just tossed in at random. And Mark says, well, you could divide them this way. What do these things all have in common that is different from those things? The things at the top are all round. The things at the bottom are not round. They're anything but round. How did they get to be round? How come these things are round? Objects that are big enough that they have enough gravity so that they will pull anything that's not round and pull it into a shape that is round. Well, what stops something from being round? This is my iPhone. My iPhone is not round. Its self-gravity will never make itself round because its internal strength, the bonds between the atoms that make up this object, is stronger than the force of gravity holding it together. A droplet of water is round because the force of surface tension is what makes it round. But if I add a detergent to it and destroy the surface tension, it can be any kind of irregular shape until it hits the ground. An object that's big enough, you see, as an object grows, the physical strength of the atom bonds doesn't change, but the strength of the gravity does change. And eventually you're going to get to a point where the gravity is strong enough that it can overcome the strength of the bonds. And if I made an iPhone big enough, its weight would eventually pull itself into a sphere. And if we could estimate some way what that mass is to have enough gravity to pull it into a sphere, we could say that's the boundary between planet and not planet. The interesting thing that Mark points out is that objects that are massive enough to pull themselves by their gravity into a round shape also are massive enough that they can release energy from being pulled into shape or contain energy from the radioactive decay of elements inside, such that they get warm inside. Once a planet gets warm inside, that heat can cause the material to move around, and having things move around means that you have geologic forms. You've got the engine to drive geology inside a planet. At the very least, when the planet cools off and it shrinks, you're going to get big cracks. And you actually see big cracks in Mercury this way. If the planet gets warm enough that the rock can begin to melt, the melt will come to the surface because it's lower density than the rest of the rock, and you've got pools of lava. And that's geology. If the planet is really big, there's enough heat that it can move the rock even before it melts to start to convect, and then you've got plate tectonics. There are all sorts of different things that can go onto the surface of a planet once it's big enough to hold on to that much heat, which is pretty much the same size you need for it to be big enough to pull itself into a round shape. So, he says, the geophysics is obvious. A planet is something that's orbiting around a star, and maintains a hydrostatic equilibrium shape. That being the case, he says, there are 12 known planets. Mercury, Venus, Earth, and Mars, Ceres, the largest of the asteroids, which we have observed well enough to be pretty convinced it's round, Jupiter, Saturn, Uranus, Neptune, Pluto, Charon, and Eris, with possibilities of more to come. What's Charon? Pluto has a moon called Charon, and the two of them are of a size that the center of mass, which is orbiting around the sun, is outside of Pluto itself. I mean, the Earth has a moon going around the Earth, but the moon is so small compared to the Earth that the path that the Earth follows around the sun always is inside planet Earth itself. But for Pluto and Charon, that's not the case. You saw the way that they orbit. It looks like a dumbbell orbiting. He says they're a double planet, just like double stars are stars. That's his argument for what should be a planet. Sounds good to me. Problem's over. Let's all go home. Well, actually, there's a couple of confusing things going on. First of all, when we talk about studying the non-planets, the asteroids, we do know something about those asteroids. We know we've got images for a number of them. These two were imaged by spacecraft. This is a model based on Hubble images. And in fact, we've got a spacecraft going to Vesta and Ceres, which should arrive in the next couple of years, of which Mark Sykes is one of the members of the team that's going to be exploring the images coming back from that. It's called the Dawn mission. The curious thing about these particular three types of asteroids is this is very dark, this is rather reddish colored, not quite so dark, and this has an interesting infrared spectral feature. This spectral feature tells us that it is covered with not just meteoritic rocks, but a particular kind of meteorite called a basalt. This body, asteroid Vesta, is unique in being the one asteroid that has actually had melting going on, probably was completely melted, and then crystallized in an equilibrium way, and had the final bits of the melt erupt onto the surface. Some of them shipped off that surface and sent to Earth, and we've got the meteorites in our collection. These are from the Vatican collection, which are pieces of basalt. You can see the way they flowed. You can see the little vesicles, little bubbles where they didn't completely collapse before they melted. This is an ordinary chondrite meteorite, and it looks like it came from this kind of asteroid. This is a carbonaceous chondrite meteorite. It looks like it came from this kind of asteroid. Yeah, so? Well, a basaltic achondrite. Basalt is melting inside a planet. Melting inside a planet is geology. So shouldn't Vesta be a planet as well? Except, look at Vesta, it's not round. It's not round because there was a big impact in the southern pole, which banged it out of shape. In fact, probably what happens, we know how old these rocks are. You've got them in the lab. You can date them using radioactive techniques. They're 4.5 billion years old. They melted at the very beginning of the solar system, erupted, froze, and then after that, they never, nothing more ever happened to the body. So, this is a body that when it was young and molten, it was weak enough to form itself into a sphere and have geology, and then it froze and became too strong to pull itself into a sphere after it got banged. So, is that a planet? Is it not a planet? Is it used to be a planet but isn't anymore? What do you do with a case like that? I don't know. The other curious thing about these two guys is that I have measured the density of these rocks in my laboratory. That's what I do. That's my research. The people who have gone to these asteroids have been able to measure the volume and the mass of the asteroids. Now, density is weight divided by volume. Density is what you use to determine what something's made out of. Any kid who's had a Christmas present under the tree, and you pick up the present, when I was a kid, I was told, before you go to Christmas Mass, you're allowed to open one present. So it's very important to choose that present carefully. You don't want to open a box and turn out it's the box of socks, right? You want something that's cooler than socks. So you take the box out and you feel, well, this one's too light. No, this one's just right. When I'm saying too light or just right, I'm measuring density. I'm guessing what's inside the box by the sense of how much weight is there for a given volume. The densities of these guys are very different from the densities of the rocks that we think came from those guys. How is that possible? The density of this is about 3.5 times the density of water, but the density of that asteroid is only 2.5 times the density of water. The density of this is about 2.5 times the density of the water, but that density of that is only 1.5 times the density of water. How is that possible? It's possible if this is not a solid rock, but a pile of rubble. Piles of rubble are much looser than rocks. Think of this way. You're not too far from Lake Ontario. You've all gone to the beach in the summertime. Next time you go to the beach, find a little kid who's digging in the sand with a pail and shovel, and knock them over and steal their bucket. Fill it up with sand, and then find another bucket the same size and fill it up with water. And pour the bucket of water into the bucket of sand. And you know you can probably fit about half a bucket of water into that bucket of sand before the water comes out the top. That's telling you that half of the volume of the bucket of sand is empty space. Because the sand is loose and there's empty space between the grains of sand. Same thing going on here. We can actually estimate how much of these asteroids is empty space, about 20%. These guys, about 40%. These guys, the icy comets, around 80%. And this is true of almost all the asteroids. True except for the very largest asteroids. And I say, aha, the guys up here, where there's no density, no porosity, these are the guys that are strong enough to have pulled themselves into a coherent shape. So that's my density, and that's my definition of a planet. In fact, it's a definition of a dwarf planet. Coherent, not rubble piles, correlated with size, it's around 10 to the 20 kilograms. Vesta, that one odd case, is a mass of just at about 10 to the 20 kilograms. So it's the boundary case. But okay, there's going to be a few boundary cases, but that's the rarity, that's the exception, not the rule. And only these guys are going to be capable of heating. I think I've solved that. And that being the case, here's all of the objects in the outer solar system that people think might be dwarf planets. These are all the guys that have masses of about 10 to the 20 kilograms. Now, I'm guessing the sizes and I'm guessing the densities, but, regardless of the guess, anything about 500 kilometers in radius, 1,000 kilometers across, by this definition, ought to be big enough to pull itself into a spherical shape, and therefore you would expect to see gravity on the surface. So, how many planets are there? There are the 8 that everybody agrees on, plus Ceres, plus Pluto, and Eris, and Haumea, and Makemake, and Sedna, and Orcus, and Quaoar, and these other guys that don't even have names yet. And it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 20, maybe 21. Charon should probably be in this list too. Ceres, make it 22. Vesta, make it 23. So, we've gone from 9 planets to 23 planets. Why did people think Pluto was a planet in the first place?
Because it was big enough to pull itself into a round shape.
Because they thought that it was big enough to pull itself into a round shape. Absolutely. Well done. But there's more to the story than that. Part of the story is, when people started looking for a planet out beyond Neptune, they asked themselves, how did we discover Neptune? They discovered, the ancients knew the planets all the way out to Saturn. And then William Herschel discovered Uranus almost by accident in the 1780s. After observing Uranus for about 30 years, people noticed that its orbit was slightly perturbed from what you would expect. And someone suggested maybe there's a planet out beyond Uranus that's perturbing its orbit. In fact, I can calculate where that planet is likely to be. And they looked there and they found it. And that was planet Neptune. It worked once. Why not try it again? So they looked at Neptune and they followed Neptune for about 20 or 30 years and said, okay, if there is a planet out beyond Neptune perturbing it, what can we say about that planet? Well, it's probably here and it's probably a given mass. And so they had guessed what they thought the mass should be, about 10 times the mass of the Earth. Then Pluto is actually discovered, and the estimates of, given the fact that Pluto really wasn't very big, they said, well, maybe it isn't 10 times the mass of the Earth, maybe it's only like 1 times the mass of the Earth. But Pluto was still just a dot of light in the telescope. You couldn't actually measure it. This is based on the fact that if Pluto were any bigger, you could have measured it. And you can't, therefore it must be no bigger than that. Eventually, Pluto would pass near a faint star, and they say, okay, when it blinks the star out, we'll know what the size of Pluto is, and the star didn't blink out. I guess Pluto is smaller than we thought. Well, around 1980, these two guys made a plot of all the estimates of the mass of Pluto as a function of time from the 1840s when it was first predicted until the 1960s. Finally, in 1978, it was discovered that Pluto had a moon. And from observing that moon, they could calculate the mass of Pluto, and it's way down here, less than 1% the mass of the Earth. And they said, you know, at the rate the mass of Pluto is shrinking, it's going to disappear by 1984. They were joking, of course. They were being funny. But the point was, if you plot the masses of the other planets on this scale, Earth goes up 2 stories from here. Mars fills the graph. Mercury fills the graph. The moon, Earth's moon, is still pretty big. Pluto barely registers. Now, is this the same thing as that, or that, or that? And if not, where do you draw the line? We now have estimates for the radii of the moon, and a moon of Uranus, or Neptune, called Triton. And Eris, that newly discovered object that started everybody wondering, is Pluto unique? And Pluto, and Charon, its moon, and Sudden, and Makemake, and Hamo said, what's wrong with Haumea?
Not round.
It's supposed to be round, but Haumea isn't round. It's actually shaped like a cigar, like a football. How do we know that? We don't actually see it. What we do see is that it is spinning very quickly, and its brightness changes very dramatically as it spins. And the only way we can explain that is to say that it is elongated so that sometimes you see a lot of it, and sometimes you only see a little, and then you see a lot, and then you see a little. And if it's spinning that fast, you could explain its cigar shape, because anything that big spinning that fast would pull itself out into an ellipsoid like this. So the idea that a planet is something that's in a spherical shape, well, we really mean an equilibrium shape, or we really mean a hydrostatic equilibrium shape. But suddenly that's a whole lot harder to explain in the Jay Leno show. There was another peculiar thing about Pluto. Back before 3 years ago, when I would teach astronomy to my undergraduates, I'd say, all the planets orbit the sun in the same direction, and all the planets orbit the sun in pretty much the same plane within 1 degree, except Pluto. And all the planets have pretty much circular orbits, or close to circular orbits, except Pluto. And all the planets are in orbits that don't cross any other planet's orbit, except Pluto. Pluto is in a very peculiar orbit. It's tilted. It's sometimes inside the orbit of Neptune. And it's in a 3-to-2 resonance. What does that mean? The closer you are to the sun, the faster you go around the sun, and of course the shorter the path you've got. So Neptune can go around the sun twice for exactly the amount, or 3 times for exactly the amount of time that it takes Pluto to go around the sun twice. Now, this kind of exact resonance doesn't happen by accident, you would assume. The odds are phenomenally low. If there's a resonance like that, you want to know why. And you can actually show that once there is this resonance, if something should happen, if Neptune should move for some reason, Neptune is big enough that it would move Pluto as well to maintain the resonance. If we looked at that same list of dwarf planets, and that same radii, you notice that the perihelion, the closest approach to the sun, and the aphelion, the farthest approach to the sun, are very different for all of these. Look at 76 and 942. In other words, it comes as close as, this guy would come as close as 35 astronomical units, and then go out to 52 astronomical units. It's crossing, each of these are crossing each other's orbits. And all of them are wildly tilted compared to the plane of the sun and the other planets. So you're beginning to recognize that these guys are a bunch that look a lot like each other. And when you look at their orbits, they don't look like planets. This comes to a more significant point about how planets, we think, are made. I don't know how planets were made. I wasn't there. The best I can do is look at the planets we've got today and say, what can I say about how they might have been made? I know that planets are in distinct regions of space. I know that whatever the planets were made out of probably at one time was spread out around the sun, probably more or less where they are now. In other words, if I took all of the mass of Venus and ground it up into dust and spread that dust around in this yellow ring that goes from halfway to Mercury to halfway to Earth, I could calculate from the mass of Venus how dense, how thick that ring would be in order to account for all the mass that I know is in Venus today. And likewise for each of the other planets. That's the minimum amount of dust that must have been in that part of the solar system. When I realized that the solar system was formed out of a ring not just of dust but also gas, because the sun is made up of dust and gas, Jupiter is made up of dust and gas, the dust is only 1% the mass of the gas, and I put together rings that include all of these factors, I see that there's a nice progression. The disk of gas and dust gets thinner and thinner as you move outwards, with a couple of odd things. The asteroids are a factor of 10, 100, 1,000, 10,000 lower than the amount of mass you would expect for a nice even pattern. And Mars itself is low by a factor of 10 or so. Why would the asteroids and Mars be so small compared to Earth and Jupiter? Our best idea so far in how the solar system was formed is that we had this cloud of gas and dust. We know they exist because we see clouds of gas and dust around other stars nowadays. We didn't know that when I was a student, but with Hubble we've seen these disks. You have a cloud of gas and dust. Closer to the sun, the cloud is mostly gas because it's hot and some of the dust evaporates. As you go further out, the cloud gets colder, so more things can condense out until you reach the magic point where it's cold enough for water ice to freeze into snow. When that happens, there's so much more water than anything else, because water is just hydrogen and oxygen, and there's much more oxygen in the universe than there is silicon or iron. There's so much more water around that this water suddenly forms itself into a planet. It finds other bits of water to stick together, and you have a snowball starting. And the snowball is big enough to capture the gas that's still in the cloud of gas and dust, and that's why we have Jupiter, which is a ball that looks like an ice ball at the center covered with a cloud of gas and dust. Once Jupiter is formed, it does an interesting thing. Remember when I talked about resonances? If you've got an asteroid here and Jupiter here, both of them going around the sun, but they're going at different rates, so the asteroid catches up to Jupiter. When it gets close to Jupiter, Jupiter's gravity gives it a yank and tries to change its orbit. Sometimes the yank will try to change the orbit out that way, because that's where they met. If they meet over here the next time, then the yank pulls it out in a different direction. And if they meet at random places in their orbit, the average effect is nothing. It all cancels out. But if they meet in the same point of their orbit, this inner guy that gets yanked a little bit, gets yanked a little more to exactly the same place, yanked a little more to exactly the same place, eventually the orbit gets very, very elongated until it might actually get really close to Jupiter, and then Jupiter's gravity can throw it out of the solar system entirely. Is there evidence that this happened? You look at the asteroids today, and the places where Jupiter is in a 2-to-1 or a 3-to-7 or a 2-to-5 resonance are exactly the places where you hardly find any asteroids. This idea of a resonance is something that every kid in this room is familiar with. If you ever sat, or anybody who's ever been a kid, if you go to the swing set, you can immediately calculate from the length of the swing what the resonant frequency of that pendulum should be, and rock your legs at exactly the same frequency. Well, you don't actually calculate the length of the thing. You just sort of rock your legs. If you just sort of kick your legs back and forth, nothing happens. But if you rock your legs back and forth at the same frequency that the swing wants to swing because it is a pendulum, then it's going to get bigger and bigger and bigger, and everybody knows how to pump a swing until eventually it goes over the top and you turn inside out and you die. We all learned that when we were kids, right? The same thing is happening to these asteroids that are being rocked by Jupiter. Notice something else, however. There's this, Jupiter is out here at 5 AU. There's hardly any asteroids there. How did that happen? That happened because Jupiter probably started out farther out, and there were asteroids here in a 2-to-1 resonance. And Jupiter ejected all of them. But if they get ejected outwards, then Jupiter has to move inwards. And so now the resonance point is there, where there's more stuff to get ejected out. So Jupiter goes in. There's more stuff to get ejected out, so Jupiter goes in. And Jupiter apparently marched in and further into the solar system, ejecting all of these asteroids and most of this stuff. Until it finally got there, and there was not enough stuff left to eject out for Jupiter to have any effect, and it's kind of stuck where it is. And that explains why there's hardly any stuff in the asteroid belt compared to what you would expect, and even why Mars itself is lacking stuff. And that's where comets come from. The Oort cloud of comets, that cloud of stuff at 10,000 or 100,000 AU, in all weird directions, you only can explain why there's going to be a body of stuff, not just in the plane of the solar system, but in all weird directions, if it was just thrown out at random by close approaches to Jupiter. The Oort cloud is all of the stuff that used to be inside Jupiter. But there's also a Kuiper belt closer into the sun that was the leftovers of stuff that never got made into a planet. Now, realizing this, a couple of scientists in Nice, France, came up with the Nice model, which is a really nice model. It's a mathematical model that looked at what happens when Jupiter and Saturn and Neptune and Uranus were all in different positions at the early solar system, and these are the fragments that had not yet been made into a planet. And I've got a young scientist here who's trying to say that you got that wrong. Yeah, I said Jupiter and Saturn and Neptune and Uranus. Because this is what happens when they run the mathematical model. As Jupiter moves in, it reaches a point where it gets into a 2-to-1 resonance with Saturn, and did you see what happened? These guys got yanked way out. Neptune actually gets ejected out to beyond Uranus. And all of these outer bodies get thrown away. If Neptune, let me go back and see if I can do that again. Okay, dark blue, purple, dark blue, purple, dark blue, purple, dark blue, purple, and now they get yanked and dark blue and purple switch positions. But remember, Uranus and Neptune are really big. Anything that was in resonance with them, as they move out, will also move out with them. So, what bodies that are out here that are stable are probably bodies that are in a resonance with Uranus or Neptune. Do these bodies even exist? Well, 30 years ago, this was an excellent image from the Palomar Sky Survey of a random part of the sky. But with the Keck telescope, we can now see a whole lot more detail. And among the detail, we can see the motion of red, green, blue, blue, green, red, because they switch filters between images. Objects out in the outer part of our solar system. You see them moving. You know why they move in that picture? It's not because that's the motion of that little object around the sun. It's because the Earth has moved from image to image. It's actually the parallax motion of the Earth. That tells us that these are objects out beyond Neptune, but still inside our solar system. Now that we've discovered Kuiper belt objects, we can plot up where they lie, and we can start looking at all the different orbits that they have. There are a whole lot of these objects that are nice circular orbits around the sun. There are a bunch of these objects that are in orbits that are in 3-to-2 resonance with Neptune. Not just Pluto, but a whole bunch of other smaller guys that got caught in that resonance, and as Neptune moved out, they got dragged along, and then the resonance captures a new guy, and it gets dragged along, and eventually there's a whole population of guys that are called Plutino orbits. There are some objects that are really scattered, and some objects that are finally scattered back into the solar system. So what happens is, these blue guys are the original objects in the outer solar system. Neptune marches along and sweeps up most of them into this one region. These are all the Plutinos. And then starts perturbing objects out. And first they get perturbed further and further and further out. And then something happens that sweeps them in until they become comet-like objects here. So there's this conveyor belt of perturbations by Neptune and Uranus that move the Kuiper belt objects first out and then back in. And here's Pluto, just one of an entire population of Plutino-type objects. Clearly, Neptune is different from Pluto. Neptune, when it moves, makes Pluto move along. Pluto, when it moves, is yanked back to where it was by Neptune. Neptune controls Pluto. Pluto does not control Neptune. And this is something you see even in models for the formation of planets. This is, again, is a computer model, a calculation. Here's a planet growing in one of these clouds of gas and dust, and you can see that it's beginning to suck up all the material in its feeding zone, and also to control at various resonance points outside what's going on. So when we look at bodies like Pluto that are, of a size bigger than any asteroid, and recognize that we're now discovering new objects like this planet X, which we now call Eris or Makemake or Haumea, these newly discovered objects that are roughly the size of Pluto. Eris is actually bigger than Pluto. They're still in extremely odd orbits. Sedna is my favorite. Here's Eris, and there's Pluto, and this is Sedna. Clearly perturbed into a wild orbit. And they just fit on this plot along with everything else. So the argument here is, no, these aren't planets. These are something different. And it's not the first time that the number of planets has been dropped. Once we realized that the sun and the moon are not planets, with the Copernican system, we went from 7 planets to 6. As we added planets in the early 19th century, every asteroid was considered a planet until they got to about 24, and they said, no. The asteroids are different from the planets. And we dropped down to 8 planets. They added Pluto for a while, and then they said, no, Pluto and the things like Pluto, they're not really planets either. Who finally makes the decision? The answer is the IAU. Who's the IAU, and why do they get to make the decision? The International Astronomical Union was this group of astronomers formed in 1919, and their job is to come up with the arbitrary but necessary divisions so that when you say that a star is in the constellation of such and such, it's the IAU that drew the boundaries of where those constellations are going to be. It was an international organization founded right after World War I, and so it was founded in a sense of being a nations making these decisions, because in those days, most astronomy was done by nation, by a national observatory. And so every nation has its vote. And the Vatican is a nation. And the Vatican is a member as a nation. And I actually attend the IAU as a representative of the Vatican city-state. How does the IAU make its decisions? Well, they have an executive committee. The executive committee appoints divisions, commissions, and working groups. There's a division called Planetary System Sciences, and 2 commissions, one involving minor bodies and one involving planets and moons. And this was the crux of why the decision had to be made in the year 2006. An object is discovered which is bigger than Pluto. Who is in charge of naming it? Who is in charge of keeping track of the data? Is it the Committee on Small Body Nomenclature? Or is it the Working Group of Planetary Surface Nomenclature? Is it the Small Bodies Committee or the Planet Committee? Or some combination of the two? Somebody's got to keep track of the data. Somebody's got to come up with a name. The fellow, Mike Brown, who discovered a body that was known as 2003 UB 10303. That was the number is just tells you when they discovered it and what month they discovered it. They wanted a name. They wanted to be able to give it a name. They wanted to know, do we give it a number like asteroids get, or do we not give it a number because planets don't get numbers? Do we keep track of the data in the JPL very detailed listing of data of orbits because you have to have lots of extra terms in their data because the orbits of planets are important? Or do you just keep track of the general positions of the bodies, knowing that these orbits are likely to be perturbed by the planets, so there's no point in keeping higher precision to them? These were very practical questions that the IAU needed to decide. So you wanted a committee that included a representative, presumably the president of Commission 15 and the president of Commission 16. From the year 2003 to 2006, I was the president of Commission 16. How did that happen? I'd like to say it was because of my brilliance and my tremendous reputation in the field. And if you want to believe that, I won't disillusion you. But back in 1994, I was at an IAU meeting of Commission 16, the commission involved in planets. And back in 1994, the only people really interested in planets from an astronomical point of view were people from countries that had spacecraft missions going to planets. So when they put together the organizing committee of the officers of Commission 16, someone said, you know, everybody in your commission is either a Russian or an American. The IAU is not going to like that. You got to have at least one token European on the commission. And they looked around in the room, and there was nobody in the room from Europe. And then Micah Hearn says, Guy, you're from the Vatican. That's Europe. So even though I'm from Detroit, I was the token European put on the commission, and therefore the rotation meant that by the time 2003 to 2006 came along, it was my turn to be president. This is what we were told to do. The chair of Division 3 said, we have to come up with a definition. It's not to answer the question whether Pluto or Sedna is a planet, but to come up with a more general definition. So they put together a working group. And the working group had people from every country, every continent, male and female, and it was much too large a commission. It was impossible. They came to absolutely no consensus. It divided not into two, but into three. It had three different definitions. Nobody would agree to give up their definition for the others. And each of the definitions, out of the 19, it was like 6 to 6 to 6. It was a mess. The year 2006, and the big meeting that occurs every 3 years, was coming up. We've got to come up with a definition. So they put together a new, much smaller commission, and they said, including a historian, Owen Gingrich, including a journalist, David Sobel, to represent the common folk. And they came up with a proposal. Object is a planet. If it goes around a star, but it's not a star itself, that means that brown dwarfs and really, really big things are not planets. Okay. Large enough that it has hydrostatic equilibrium, we know what that's all about. And you have double planets. The result was the 12 planets. This is what Mark Sykes said at the very beginning of this talk. This was proposed to the IAU. When they got to the IAU, all of the scientists who work in celestial dynamics made all the arguments that I just made. Hey, we're dynamicists. We also study planets, and those little things like Pluto are definitely not the same kind of character as the big guys who control, by their gravity, what's going on anywhere near them. So planets have to be things that accreted, like that model showed, and really sucked up nearly everything nearby. And they have to perturb other planets, maybe even perturb the star that they're around, and not be perturbed. And this says there's only 8 planets, not Pluto. This sense of perturbing and not being perturbed has an interesting result. When you ask them to actually, mathematically, what do you mean? This is the kind of boundary area that one of those guys, dynamicists, came up with. They said, anything above this line is a planet. But the line changes as you go out into the solar system. You need more and more and more mass to clear out the solar system when you're farther out. And more and more mass to be able to scatter things. So that by this definition, something the size of the Earth out at Pluto's orbit would not qualify as a planet. Now, is that right? Well, so far we haven't found anything out there yet, so it's not a worry. But remember Sedna? Remember Sedna's really weird orbit? The easiest way to explain Sedna's weird orbit is to suggest that there's some Mars-sized object that perturbed it that we just haven't seen yet. And if you go far enough out, it's not impossible that there could be a Mars-sized object at 50 or 100 AU. So this is a problem lurking in the distance. So, at the IAU meeting itself, there were 3 times people got together to really argue about this. The first was Friday afternoon. Among the planetary scientists, they said, okay, we'll have both definitions. We'll have 3 classes of objects. We'll have planets, we'll have the asteroids, and in between we'll have something that we call dwarf planets. But we want to make it clear that dwarf planets are not really planets. The IAU president, a few days later, knows that this is going to, Jay Leno is going to have a field day with this. Because no one's going to be able to understand this perturbing stuff. So he says, can't we come out with some way of it? And the dynamicists are furious. So they said, wait a minute. We're the scientists. You're trying to impose something just for PR, but this is where the science is leading us. So they bring in, that evening, Jocelyn Bell Burnell. Who's Jocelyn Bell Burnell? Maybe you remember the story back in the 1960s of the discovery of pulsars. There was a radio telescope in Britain that was being used to measure something else, and the graduate student involved noticed a regular blip in a certain part of the sky, called up her advisor and said, there's something really strange going on, and it's a very, very regular blip. And they originally called it LGM-1, LGM standing for Little Green Man. Because they thought, maybe this is some intelligent... But it turns out to be what we now call pulsars. Pulsars are incredibly important. This was such an important discovery that the Nobel Prize was given to the advisor of the person who made the discovery. The person who made the discovery was Jocelyn Bell. Jocelyn Bell was getting all this sympathy. How come your advisor got the Nobel Prize and you didn't? And she got up in front of everybody and said, he got the Nobel Prize because it was his experiment, it was his interpretation, he was the one who figured out what it was. I was just the one who happened to be sitting next to the chart recorder. He deserved it, not me. As a result of saying that, she's more famous today than he is. Because nobody remembers his name.
Yeah.
And she's one of the most trusted astronomers in the world. Someone whose integrity is unquestioned. So a committee was formed to write a definition. The chair of the committee was actually this guy. His name is Chris Corbally. He's a Jesuit priest from the Vatican Observatory. So you see, the Pluto definition really is a Vatican plot. And that's Jocelyn Bell. And this was the chair of the original committee whose definition got shot down. And you see her here with the stuffed dog. She came out to explain to the entire assembled astronomy group how we're going to do the vote. And she had 3 props. One was a big beach ball. And she said, this beach ball, this is a planet. This is a major planet. Everybody knows what this is. She brought out a bunch of gravel. She threw it on the ground. And she said, these are small solar system objects. Everybody knows what this is. And then she brought out the stuffed dog, Pluto, and a box of cereal, Ceres, and said, these are what we're going to call dwarf planets. First vote. Vote 5A. We resolve to split objects into 3 classes: planets, dwarf planets, small solar system objects. Everybody agrees there are 3 classes of objects. The evidence is overwhelming. Resolution 5B. We're going to add the word classical to the first group. So there are classical planets, dwarf planets, and small solar system bodies. At this point, she pulls out an umbrella. She opens the umbrella and puts it over the big ball and the little stuffed dog. The point of passing this would to create an umbrella class saying both of these are planets, and therefore all of the work would be handled by the Planet Commission, not by the Small Body Commission. This was the critical vote, but it failed. It failed by a considerable vote. 200 in favor, 300 to 400 votes against. It was so overwhelming that they didn't bother actually taking a complete count. It was clear the majority of the scientists there said, no, we're not going to say these are classical planets. It's like classic Coke. I'm sorry, they're planets. The result, Pluto and Eris and the other 12 new candidates are dwarf planets, but they're not considered a planet. The last vote was, well, do you want to recognize Pluto with a funny name? And we're going to call them Plutonian? No. Somebody said, could we call them Plutons? No. Pluton is a word in geology, and what's more, Pluton is the French word for Pluto. So that would not be a good idea. The final result, Pluto is special. Its class of objects will be related to Pluto, but we don't know what to call them yet. The word that finally was adopted was Plutoid, which is nobody uses, so it doesn't really matter. It's kind of like hemorrhoid, I think. And as predicted, there's outrage and horror. My favorite being this resolution passed in the state of California. Whereas Pluto, named after the Roman god of the underworld and affectionately sharing the name of California's most famous animated dog, has a special connection to California history and culture, and whereas downgrading Pluto's status will cause psychological harm to some Californians who question their place in the universe.
Pluto's still a planet.
We all lived through this. We all know what this is about. The cartoon here, I don't know if you can see it in the back from Foxtrot. I don't understand how a small group of astronomers can on their own declare Pluto is not a planet. All the astronomers from Earth were too. Who put them in charge of the solar system? Where were the Plutonian astronomers? Shouldn't they have had a voice in this? Taxonation without representation, I say. There was one last issue to face. What are we going to call that thing that Mike Brown had discovered? Now, Mike Brown, when he makes a discovery of a new object and he doesn't know yet if it's a dwarf planet or what, and doesn't have a name for it, will invent a name just for himself and his group. It's not supposed to be an official name. It's not a name that anybody should know about, but these things leak out. So he's had objects that he's called Easter Bunny. He had an object he called Santa Claus. This particular object, because he thought it might be Planet X, he called among his friends Xena, as in the character from the TV show. Obviously, Xena's not a real classical god or goddess, so they had to come up with another name. They put together a committee which included the entire working group of planetary surface nomenclature and the working group, the Committee on Small Body Nomenclature, acting together as one super committee. He proposed the name Eris. Eris is the Greek goddess of discord and strife. She was the one who tossed the apple that started the Trojan War, if you recall. Everybody agreed Eris was a wonderfully appropriate name for this object because it caused so much discord and strife. But by this time, he had discovered that Xena, now Eris, had a satellite. So he said, well, what about the name Dysnomia, which is the spirit of lawlessness? Now, is there anybody in the room who is a fan of Xena, the show? Who plays the role of Xena? Lucy Lawless. And that was his final little joke. So that's why Pluto is a dwarf planet, and an absolutely lovely dwarf planet. When it was considered a planet, it was an ugly duckling of a planet. But now that it's a dwarf planet, it's the perfect swan of a dwarf planet. Thank you very much.
All right, we got a lot of things going on, but first, how many of you still think Pluto's a planet? Come on! See, it never works.
Yeah, science,
You
fortunately,
can't
is not-
educate them.
Science is not decided by vote, usually. Except in this case it was.
Yeah, right, there you go. Okay. So did you want to do some questions?
Yeah, if anybody's
Let's
got
do some
questions about this, a few. Yeah, in the back, sure.
Why do major planets tend to be in the same plane? But why don't you just randomly distribute it around the spherical distribution?
This week's theory, and we've had, 300 years of theories of planet formation, and they do change, but this one has been around for actually about 50 years, and we're pretty sure it looks reasonable. It says that stars are formed out of clouds of gas and dust. Okay. You had an old star that blew up and blew all this gas and dust into the universe, and then eventually its own self-gravity pulls it together, and the cloud gets denser and denser. But every object in space is going to have, for whatever reason, a slight amount of angular momentum. It's going to have a slight tendency to spin. Just because it's going around the center of the galaxy means it has a slight tendency to spin. As it shrinks, it's like the skater pulling her arms in, it spins faster. As it spins faster, the centrifugal force of the material stops things from falling in the plane that it's spinning, whereas the axis around which it's spinning, there is no centrifugal force, so that stuff can collapse down to the center. The result is you wind up with a disk, like a frisbee, of spinning material. And all the planets, therefore, should all be going around the center sun in the same direction and in that plane. So far as we know, pretty much that's what we see in our solar system, in the moons of Jupiter, in the moons of Saturn, in the moons of Uranus, the major moons at least, and in the planets that we've seen around other stars. Now, the last step of that theory was you would assume that there's a nice gradation of size, and we don't see that in planets around other stars. So our theories are not perfect. But that appears to be why the planets, and that happens to be the same way that the sun itself spins. So it all looks like it came out of the same pot that collapsed down that way while it was spinning.
You can just repeat the question.
Okay, so the question was, why are all the planets going in the same direction? Yeah.
Is not the Oort cloud spherical in shape?
The Oort cloud is spherical in shape. So the Oort cloud, that says the Oort cloud is not part of the primordial cloud of gas and dust. And remember, the way I explained the Oort cloud was to say that it was thrown out of that plane because these are objects whose orbits got distorted to the point where they got close to Jupiter. Now, if they get close to Jupiter, but just a little bit above Jupiter, Jupiter will fling them out of the plane, one way or the other. And that would explain why the Oort cloud now has these bodies in all sorts of directions. Whereas the plane of the planets and the asteroid belt and the Kuiper belt are pretty much in the same plane, to within a couple of degrees.
Thank you.
Other questions? Yes?
Yeah, I recently read that there was now a new decision on what made a moon a moon. A lot of Saturn's moons are no longer moons.
I haven't heard that one. And the trouble is, I'm in the working group on planetary nomenclature. I'm not in the working group of small body nomenclature. So, I mean, I'm on top of what's going on in planets, but I'm not on top of what's going on in the small bodies. I hadn't heard that. That's interesting. I'm gonna have
It was
to.
in the Sky and Telescope last month.
I'm gonna have to look that up. Actually, moons are considered part of. I don't know what that's about. I'm gonna have to find out more about that. It's the first I've heard of it. Okay. Other questions? Yes. Okay.
He wanted to know what, as you find objects out in the Kuiper belt, if it's going to change into more definitions.
Will there be more changes as we find more things in the Kuiper belt? I don't know, because we haven't found them. But I wouldn't rule it out. If we found something really big, like the size of Mars, out in the Kuiper belt, would that make people to go back and rethink the definition of a planet? It might. Part of the trouble was that Pluto was a planet back when we thought that Pluto had 10 times the mass of the Earth, or 1 time the mass of the Earth. And by the time we realized it had like less than 1% of the mass of the Earth, it was easy to say, nah, I don't think it's a planet. What if it did have something the size of the Earth? By this definition, it would not be a planet. Would that sit right with... I don't know. So, nothing is fixed. Nothing is, The future depends on what we see. And will this definition work for objects around other stars? We won't know until we really get a good inventory of what's in around other stars. So, stay tuned. You could be the guy making that decision. Because, by the time you're my age, we may have
Yes, the
discovered
right
these
suit.
things. Okay, I think that's one last, and then we'll, yeah.
I have
Two questions, okay.
two.
Say what again?
What's your favorite planet?
What is my favorite planet? My favorite object is probably Europa. I really like Europa, but it's not a planet. When it comes to planets, it depends. It's like asking a mom, what's your favorite kid? Whenever it's whatever one I'm working on at the moment, I'd have to say. I like Earth. I really like Earth. But I've got a special attachment to it. And your other question?
My other question is, I heard that there's another planet. There's like 10 now.
There might be 10 planets.
Yeah.
People have been looking for a 10th planet for a long time. The one that they thought might be a 10th planet was this Eris. But as soon as they found Eris, they found 3 other ones. So whatever the number of planets is, it's not 9, and it's not 12. It's either 8 or it's 25. But the idea that there could be something really big way out in the outer solar system, we can't rule out yet. There could be something pretty big at 100 AU. It would change our understanding of how the planets were formed, but that wouldn't be the first time that's happened. So there's lots to still learn in the solar system. The more you learn, the more you realize there's stuff you thought you knew that you don't know. So, which is part of the fun of doing this stuff. I'd like to thank all of you guys for coming. And